Hello. In this video, we're going to actually do a simple introduction um, to parser combinators. So, what is a parser combinator? So, if you followed my channel, you know that I've been doing a compiler in Rust, and so I was mostly stuck on the parser part because I was using the low-level approach with the state machine, and it was getting a bit too complicated and too coupled code base. So what I did, I looked for alternate solutions to this problem, to this parsing problem. So if I want to do an introduction to what is a parser at first, in case you don't know, you probably know, but so the parser is just a tool that converts a stream of bytes or tokens um, into a structured tree. Sometimes we call them, I mean, in my understanding, they are abstract syntax trees. So basically, if you write if something bracket, then some code bracket close, else, these all become for example, imagine a class or a struct created for this, have this, and for example, has a condition, which is some expression, has a then block, and has an else block. So basically, this is what parsers do. And we most of the times we do parsing in general because it's really easier for programs to work on data structures like trees other than in comparison with the strings in general when we write the source code into or any other actually thing. So we have three kind of parsers. So we have generated parsers that are generated from a grammar file. Um, there are examples of it like Yak or Antler tool, which you write your language, your syntax you want to write, you want to parse as some kind of special grammar, and it will generate a state machine specific to that case. So it's the most high-level solution and probably the easiest to get working. Next, we have the parser combinators, which we are going to talk about in this video. And also we have the state machines, which are the most performant but hardest to write parsers that are created based on a state machine. They're completely written in hand, and it's based on, so if you have the stream of tokens, it's based on, you have a cursor, you go forward, sometimes you go backward, you need to store states of before um, cursors, and it's actually a bit hard and really hard to read, but it's the most performant one. So what is the parser combinator? The parser combinator is built from combination of small parsers, and it's really a functional programming concept, and it's coming from there. It's coming from functional programming word. So it's basically says that if you have a function that parses just a small amount of your syntax, and the smallest amount of syntax that you can parse is probably um, a character. So if you have a program, if you have a function that parses just one character, you can combine it with some combinator functions. You can combine it together and create a massive parser out of that just one character parser, and you can build a complex parser that parses a whole programming language. So it was mentioned to me. I've heard before about the parser combinators, but I didn't think that they could handle big programming languages. But my good friend Dr. Lazy on Twitter mentioned to me that actually language Elm is using parser combinators for parsing. So I took a look and I was really hooked because of the code that it will because of the way you write the code. It's really simple and really amazing. I will show you in a bit. But so what are the pros of parser combinators? They're the most readable ones. Um, I actually want to argue that they are more readable than generated parsers. because I mean they're just code. So if they are written in a programming language that you know, you can just read them. But the grammar files are a complete different programming language. So they're the most readable ones, I think. They're really easy to write and reason about, and you can write them in any language. So for example, those parser generators, they work for certain languages, not all of them. For example, I think Yak generates outputs C code, I think, and Antler has multiple targets, but it's limited. But parser combinators is just a way of thinking. It's you can apply it to, I think, every function, every programming language. Also, you can always opt into the low-level state machine if you want performance for a single part of your application, your parser. You don't need to rewrite everything. If you just want performance for one part, you can just opt into the low-level state machine, because as you will see, and as we are actually working in with the functional paradigm in our minds, most of the data is immutable, so it's really safe to just change everything in a function. So let's take a look at the parser we have now for Luki. So let me zoom out a bit. Okay, so this is our parser, and this is in a branch. I've still not merged this, but this is in a branch, and so we have our usual objects. So we have an enum that contains anything that we could parse. It is basically a hack for, you know, not necessarily a hack, but it's a way for me to to create functions that have the same signature, so that way I can combine them together, and I will show you how and why. But this is basically a wrapper for everything that I could parse. So if I parse a char, it's a char. If I parse a uint, it's a usize, int, float, string, keywords, identifiers, booleans, lists, declarations, function calls, and nothing. There's also parsers, which is really naively implemented. I'm gonna really improve this part, hopefully. But let's take a look at the most basic functionality, which is this one. This is parse char function. So what it does, parse char function takes a character and returns a function. So it's a higher order function. So it returns a closure in here, and what it does is it checks for the input len. It checks if that in our input, in the input that passed into this closure, there is at least one character, and if there is, it checks if that the first character, only the first character, nothing else, only the first character matches this input character that we passed into the function, right? So, and if it's okay, it will remain the remaining unparsed, untouched part of the input, and also return what it has parsed. So this is basically the signature of all parser combinator functions. In parser combinator functions, all of them takes a string as an input and return a tuple, basically, of string that is remaining, and also an object that is parsed, right? So let's go into parse char again. And so, and also if it couldn't match the first character with the character we give it, it's just going to return error. So that is basically the most low-level thing we would write. After this, we just combine versions of this parse chart together, and you will see how. So let's take a look at the small one. For example, the white space. So for white space, so we have multiple kinds of characters that represent a white space, right? So we have space, tab, and new line. Well, I just support these. So as you see, and you could probably guess, for each one, we are calling the parse char function that generates a function or creates a function for us, so that this sp, which means space, tab, and new line, are all functions that take a string, check if the first character is their respective character. For example, this checks if the first character is the space, this checks if first character is tab, and this checks if the first character is new line. And they will return the result. So what is any of in here? So any of, as its name suggests, is basically a way of combining these together. So I'm passing all of these three to any of, and any of is one of the most used and most popular combinators out there. It has many names, but the concept is the same. Basically means any. So I give any of bunch of parsers. I don't know the number, and I give it and I tell it, okay, try the input with all of these, and the first one that was successful, return it. That's it. So when I call this for any white space, it will check the input first for space, if the first character is a space, then it checks for tab, then it checks for new line. Each one that is successful in parsing, basically that finding that the first character of the input is the respective character, it will return an OK, and basically, and you know that we remove it from the string, from the input. So that is this. So how it can help? I mean, if you're keen, you know that this is still parsing just one character. It's not parsing more than one character. So this is the second function, and actually these are old. I don't need these lifetimes anymore. Okay, so this white space now, so any white space returns a function. So any of also returns a function. I forgot to mention. Any of takes bunch of parsers, smoosh them together in this closure that you see is fairly simple. Just for loops over them, runs the parsing, and returns a new parser. Okay, returns a new function which is a parser. So what is white space? How we are parsing any amount of white space in our program, in our parser. So we are using another combinator, which is also one of the most popular ones. There are other names of this, but I call this 0 or more. Also, you can think of it as optional. So 0 or more takes a parser, and in either way, it will return OK. So it's not important for this, for example, to be able to successfully parse something, right? So it would always return OK. And actually, I think this code is a bit problematic, but I come to that later. But so it will just try to parse as many as it can, and if it couldn't even try once, it's okay for it. So for example, if it tried and failed, it's okay. It will, actually this code is okay. So every time it tries to parse the input using the parser, if couldn't, just returns the result. So this is 0 or more. So basically now you can see our white space now is a function of combination of 3 or 4 functions. Basically we have 3 functions in here, then we do another any of over them, and then we do a 0 or more over them. So now this becomes what we want to test, what we want to use. So now if we take a look at the end of this file, there is this test, I think, for white space. Oh, I didn't write any test for it. Okay, we can take a look at the. Actually, let's take a look at the float. Float is a fun one. So float is a bit. The code is not that clean that I want, but it does the job. So what it does, it tries to first. So every float number, you agree that every float number is an integer, a dot, and another integer, or another uint, we would say, because so in Loki the difference between integer and uint or unsigned integer is in the terms of parsing. Ints can have signs, uints cannot. Uints are always positive. So basically and floats can have sign. So that's the reason. So basically this is how we are going to parse a float. So we are going to do an int, which is a parser. We are going to do a parse char for dot, and then we are going to do another uint parsing. So what is int at start? Int is a parser itself. It has 0 or 1, an optional value of 1 of parser. So you can understand from the names. 0 or 1 checks if the parser applies to the given string only either 0 or only one time. After the one time, it will return. It won't check for the other parts of the string. So if it just checks for one, it just runs it once, and if it's okay, it would return. Or otherwise, it would just return. I think it would return error. Right? Yes. So okay. So we also have. So first of all, we try to parse the sign. We either have the sign or not. We check if we have the sign or not. This is not the cleanest version, but and then we try to get a uint, basically, because ints are basically uints with a sign. So we try to parse a uint, which is the before dot part of the number. We get the object. We check if it's a uint. We return to parse a basically. Oh, I did something weird. So how I'm this number. Okay, so let me check the test float something. Okay, how is this working? I actually don't know how this is working. Can I run this? Rustic test run. Okay, you know what? Just run this in a shell. Yes, we have a shell. Okay, cool. So let's go into TA Loki test. What was the name? This. Oh, there is a fly in here. So it's called parser test parse float. Parse float. Yes, it would pass. Actually, this is also a question. So it can pass. It can parse a float. You see, and it won't touch any other parts of this string, which is one of the most important things about parser combinators. They don't touch what parts they do not understand. They just don't touch it. So it can work. So actually I missed. So we were working on int function. Sorry. So the int function, after we get the sign, it will try to so we assume that ints are basically a sign plus or not plus a sign and a uint. So we take the sign, right, and then we parse a uint in here, and then we return the result if it's okay. So let's take it. So let's go back in here. So we already parsed this int. So we take the int. We also parse a dot, which is the dot notation of the float. And finally, we go and we parse a uint out of it. And we return the result. And we do some nasty shenanigans, but we return the result. Otherwise, we return errors. So basically, this is how we are doing. You see the pattern. We create a small parser. We combine it together. We create a parser. So float is basically built up on ints and parse chars and uints. Ints are also built on uints. So it's really beautiful way of thinking about parsing. For example, let's take a look at the Boolean. Boolean uses the parser keyword I've created. The keyword takes a word and returns a function that takes input and checks if it finds the exact correct keyword at that point from the start. So, for example, the true and false parsers just checks if any of true or false happens to be valid in context of the input. That is basically how we parse the true or false keyword. there are other keywords as well which we parse inside parse keyword. So for example, we are parsing a struct keyword in this string, a struct name. This is basically just not necessarily this syntax, but you get the idea. So it will just parse this. It will just remain this string untouched and returns a keyword of struct for me. We probably change this to have the specific parsed object, but not now. This is not my priority. I want to make everything work at first. So let's take a look at the expressions. So expressions are probably one of the most complicated ones, especially if you take a look at the code from before, from the version before this. So expressions can be booleans, can be identifiers, and can be strings, can be int, uint, or float, or can be function calls. And actually, let's take a look at the string, because actually string is one of those examples that I told you that you can opt into the old version and low-level code. A string is one of them. Actually, I did that not because of performance, because I didn't find a good way. I don't know a lot about Parser Combinator, so this is my problem, not the Parser Combinator pattern problem. So I changed my way of parsing strings into the old way. So I just parse the starting double quote. If I'm okay, then I try to enumerate over all characters, and I try to find the first character, the first double quote that does not have a backslash before it. So that is basically it. And if I find it, I will return the string literal. I remove the starting and end double quotes, and I return it. So this is one of our expressions. So the identifier is fairly simple. So I have these valid characters or allowed characters. This parse chars is just a helper over parse char and any of. So I'm saying that any of these allowed characters, one or more of them. I'm not basically allowing any numbers in this, because I can do this later, but I just don't want to do it right now. So it also works. There's also a version for function calls. Function calls is actually a bit complicated, but so any function call has an identifier first. So we get the identifier. Then we try to error handle and everything. So then we try to parse a open parent. So we do it, and then we do a loop over anything inside the parent. And what is that inside the parent? And we are doing a function call, not function definition. So anything inside the parent, open and close parentheses, are basically expressions, right? Expressions separated by comma. So I do this. So every time on the loop, I try to parse an expression. I change the remainings to be after this expression. So I parse an expression. So imagine we have fn 1, 2, 3, 4. So I parse this one. So the remainings are these. So I replace the remains variable I have in here with this new one, because this is the simplest one, the simplest form. So I start from here now, from this comma. I push the object, I push the expression I parsed from this. Then I have this remaining. Then I parse a comma, so I skip the comma basically. You see, I skipped it. Just again put the remaining string in the remains variable to start over in the next loop. So I loop over it and get all the variables. And finally, after we reach a variable, basically after we reach an expression that didn't have a comma in it, that didn't have a comma after it, it means that we are at end. So we also parse the closing parent, and we return the remainings and also a function call. And actually, we can take a look at the test we have in here. So it's an expression. Function calls are expressions, right? So a function call of 1 and 2 it would be parsed into a parsed object of function call with name fn call and a vector of arguments, and arguments are also parsed as expressions. So it's a uint, it's a uint. We have also a little more complex version in here. So we have a function called name that is going to be called with argument 1 and argument fn2, which is also another function call. So it's a nested one. So we do this and it works. And I can show it to you that it works. So I think it's called test parse function call. No. Test parse fn. Oh, test parse fn call, which is passing. So yes, it works. I think I did go through most of these, and I'm gonna put this video also on the Loki series, but also as a freestanding video on how to what is a parser combinator, what's the parser combinator pattern. So thanks for watching. If you like my content, you want me to continue, please like and subscribe, and also put comments. YouTube, Twitter, you can mention me on Twitter, you can send me emails, and you can open issues at GitHub. So please like this video, subscribe, and until the next video, goodbye.